That's great. So thanks very much for being here. So I want to talk about dexterous locomotion. This actually comes sort of almost coming back from where I started in 1982. It was probably before most of you were born. So maybe familiar with dexterous manipulation, which is the idea that a hand is more than a pair of pliers. A hand allows you to manipulate objects with relative motion with respect to the fingers. And so talking now about, well, what does dexterous locomotion mean? Well, that's sort of like, can we manipulate things with our feet? A lot of times what we're manipulating is the robot is manipulating itself. So the idea is moving beyond just a robot that just walks in a straight line to a robot that's going to be working either with other robots or even by itself to be able to do things other than just walk in a straight line on a flat surface. So what motivates us on this? This is our challenge problem probably for the current, for the next decade. Have a scenario with a collapsed pile of rubble, and we want to have robots that'll basically be like rats or mice and be able to burrow in there and find openings. And the idea is that when buildings collapse, concrete structures, there's voids inside where you can find people. So how do we get inside there? And to do that, we need to have something which is aiming for basically the locomotion capability of something like a rat or ant. Okay, and so let me show you what we're working to. Break this up into a couple places. Well, I just mentioned that we have lots of very cheap robots that can be made very quickly with a rapid prototyping process. They work pretty well. We've built lots of robots over the years. So I'm looking at this dexterous locomotion. So I'm going to break it up into several pieces. There's a maneuver in the plane, a terrain-coupled maneuver. Just introduced that, and Dr. Chenley will talk actually a lot more about that, where the environment is one of the things that helps you to maneuver. And then cooperative maneuver, where what happens is that we think there's always going to be situations where one robot just can't do it by itself. It just doesn't have the capability. And multiple robots doing together can do things that a single one can't. So we're starting to look at that. OK. So in plane, we've looked at a lot of ways over the last 5 years or so for how to turn in the plane. And I'm not going to spend much time on that, just show you some fun movie. This is using a tail. It's on the plane. So we get very rapid turns. Basically, it can do like this 90-degree turn in a quarter of a second. So you can do a full 360 in a second. You can see that you get a lot of maneuverability using the tail. So maneuver. And the nice thing about a tail is, as the ground is slippery, you can still turn. Okay. So terrain coupled. So now the terrain is coming in as part of the locomotion problem. So I won't say much about this. Jen's going to talk about that. But you think about it, in the environment, the robot is actually not walking on the top of things, but walking through things. So walking through grass. So actually that locomotion problem then is very challenging. It's sort of like if you were in a fluid, in air or water, swimming or flying, the medium that you're in makes a big difference. And we think it's going to be the same here for a robot, being able to go through some path like that, maybe even modify the environment. Here, you can use by bumping into things while following. Again, the terrain can be used to your advantage to help you locomote. So let me show you a few things there we're working towards. So we want to be able to maneuver on all these high slope surfaces, right? So you can take advantage of the surface. So if you want to go up to here, I could start here and bounce up. What if you want to just change your orientation? So here's an interesting thing. So I've a very simple under-actuated robot. I don't have any pitch control. But let's say I do want to pitch up to climb a wall. How can you do that? Well, here's what we've learned from our colleague Bob Full, is that cockroaches have a very excellent strategy for doing this maneuver. In 1/10 of a second, they can do a complete pitch up. Let's show you what that looks like. So that's real time. And let's show it a little bit slowed down. Runs to the wall and crash. And so if that doesn't work at the large scale, but the small scale, the animals they're very robust. They've got a very good good dynamics, and we can show something similar with our robot. So just run it into the wall, and well, so it does that pitch up. So using under actuator robot, using the environment to help it do this vertical maneuver. Good time here. Okay. Something else? Okay. Well, here's another way you can grab onto the environment. Again, if you don't have enough degrees of freedom and I want to pitch down and there's a ledge, if you can catch onto that ledge, you can take your forward velocity and convert it into a pitch down. Very rapid maneuver, and we can do that with the robot as well. So catches and swings around. So we can take advantage of the dynamics to get, I think, interesting maneuverability. For climbing, sometimes, if you don't have good adhesion, and you're going to have only friction to work with, you can apply pressure, right? So you can have greater normal force by squeezing. This didn't work all that great, but it shows you sort of what we'd like to be able to do. So this is real time. So it climbs up a little bit and falls. Actually, a very challenging dynamic problem. Here's in slow motion. It starts so faded, but you can see it is making some progress up there. What's happening? There's a low friction back, which is applying pressure to the feet, so the feet engage and climb vertically. So again, this is a terrain-coupled maneuver, and you're going to talk all about this, right, Chen? So let Chen talk about that. It's very interesting that, won't spoil Chen's punchline, but the terrain can do some really interesting things for you in terms of maneuverability. Okay, so let me spend some time on cooperative maneuver. So the analogy we'd use here is if you have one person and they come up to a fence and the fence is higher than one person, it might be hard to get over them. But if one person can boost the other one up, then they can get on top of the fence and pull the person up. So the two people are more maneuverable than one person. And we think there's something similar with robots, that no matter how many degrees of freedom you add in your robot, you're probably very likely to reach a situation where one robot is just stymied, but two robots can make progress. So we want to look at this space of how can these robots work together. And this is really where the dexterous locomotion comes in, because if you think about each robot as a finger, they can either maneuver each other or do some help one robot to overcome things it couldn't otherwise. Let's see. So this would be great, long ways away, but robots could couple together, form spontaneous bridges, form a gap. I like this. There's this trade-off, and I'll show this a slide later, sort of this trade-off between intelligence and maneuverability. So if I didn't have good maneuverability, I might have to do this great plan, figure out how to get down to the bottom and then how to come up. But if I could have these robots actually physically form together, form a new connection, then, the next robot that comes along actually doesn't need to be that smart, just follows along, right? So there's a trade-off between maneuverability and intelligence. So forming spontaneous ramps, running on top of each other, can jump up here, using cables to help each other climb, using multiple robots together. This is a very, very simple idea, but if you want to exert greater forces, you could push in here. These are all, you could think of them as fingers which are pushing that object. And there's starting to be some work in this area. I think it's a very, very rich area at Nagabal at Harvard, looking at how robots could come together to build structures, which is related. Okay. So go back to dexterous locomotion. So if you have to make an analogy here that we abstract away robots pushing other robots to thinking of them as just force sources. So here's a very simple case of two force sources, or two springs, with some kinematic constraints pushing an object. Okay, so we can think then about these spring forces working on other robots. So you have to use your imagination. These are springs working on little cubes. But I want to give you a sense of the types of things we might like to do with robots that we've done before with fingers. All right, so there's a step there where there's an alignment. So you can align against a surface. You can do a pivot. So notice there's no rotational degrees of freedom in this system. There's only translational degrees of freedom, but yet we've managed to impose a pitch, and we'll show here there was a yaw as well. That came about just from translational being converted to rotational. And here's another pitch. So you can do all of these manipulations. So this gives us some hope for that the robots, legged robots, will be able to do this. This is a very simple system. It's with passive springs. It doesn't require a great degree of sensing because the algorithm, the control algorithm, is chosen in such a way that it's inherently stable and robust to actually very, very large changes in dimensions and angles and all those things. Okay, so how would this look like for now a robots manipulating each other? So this is I would say it's a two-finger, or analogy is a two-finger dexterous hand, but it's two robots working together. So this robot needs to get up over the step. Back robot can help the first robot pitch up. This is the case using a tether. It could push as well. Then it gets close, pushes it up. The first robot tilts down, walks forward, latches on, uses a tether, and pulls it up. Right. So we have a combined dexterous locomotion where the two robots are working together. Okay. So that's in the physical domain. We're also interested in how can the robots cooperate in the sensing domain. So these robots that we're making are very inexpensive. So we can think about using them as almost a disposable probe. So you have an expensive robot, and the expensive robot might worry about where it's stepping. So if it steps into quicksand, use that as an analogy, that's going to be very expensive. The small robot could go in quicksand, and you're not going to worry about it because it's disposable. So we call this the picket robots. And should doing okay on time, so we'll have time there, right? So it's just walking. The small robot actually doesn't have any intelligence. It's got a tag on it. It's being controlled by the big robot. And now it comes across. You saw it went crazy there, right? So it's got very poor steering on the surface. This is actually a whiteboard which had water on it. And so you can see immediately the big robot doesn't need to step on that, but you can see that that's going to be a challenging area to go on. We're looking at extending that. Now, actually, we like the quicksand analogy. So you think about this pile of rubble. There's going to be areas in there be covered with full of rebar, full of wet mud, full of dust that's just impenetrable. So you may have a more expensive robot. So imagine this hierarchy of robots where there's very cheap robots, and for every 10 cheap robots, there's one more sophisticated robot, and for every 10 of those, there's another maybe sort of a master robot. So a master robot, might be something on the order of a kilogram, and then the smart robots might be the order of 100 grams, and then the really cheap disposable robots might be the order of 10 grams. So one master robot would have 100 small robots working with it. So you can afford then to say, well, I won't send this robot there, I'll send this one out. And if that robot gets stuck, that's giving me a very useful piece of information. And I might actually not retrieve that robot. It's just stuck. It's got a marker on it. It's got a beacon. And now, okay, the robot is stuck. Don't go there. No go zone. Just let it serve as a beacon. And then as you're mapping out the environment, you've already got a feature, and you know where it is. Okay. So we did a little experiment for ICRA, got this in. This is with Austin Buchan and Andrea Becci. So the idea is you have a robot here. You saw in the photo, there's this terrain hazard. And it just maps out the environment. You can see here's the dangerous area. Just maps out the environment where the robot moves is safe open space. And you can see the red circles are marking areas where things get stuck. Okay. So one more. Let's look at multimodal maneuver. So we have a trade-off between these ground platforms and flight. So actually, the small quadrotors get, they're actually pretty good, but you still think about, I've got a small opening like this I need to squeeze through. It's going to be a little hard for a quadrotor to go through. You may also need some sort of visual system for quadrotor to fly through small holes. We're underground, it's dark. You may have very limited lighting. So there's a trade-off between, do you want things that are flying and are crawling? Possibly you could bring both of them together. So this is, I think, a fun picture in terms of mobility. So you got down here in the ostrich, really fast, very maneuverable, but pretty poor flight characteristics. Up in this corner, I have the hummingbird, which is great for aerodynamic maneuverability, but surprisingly, if it's on the ground, its wings aren't working, it can't move. It can only land, and it can land on a branch and fly, but it can't walk. So great over here. So somewhere in here, we think there may be some intermediate region where things are maybe okay flyers and okay crawlers. Okay, a little out over. Okay. Or, since your robots are small and cheap, you can maybe combine the two modes together. So you can have something which is sometimes there's a ground piece and a flying piece, and they might temporarily separate and then come back together. Which you can show here. So this is showing the coordination between a ground robot and a flapping flyer. What's interesting about this is that the flapping flyer doesn't have enough power to take off at 0 speed, so it needs to have a launch platform. The ground robot needs to ramp up its velocity while the flapping robot is bringing up its wing speed, right? So if it launches at too low a speed, it'll just stall, and you have to kind of make sure those two are coordinated, and then it can take off very nicely. We haven't done the landing yet, but the takeoff looks pretty good. I think the landing's probably about 5 times harder. Takeoff's easier. So you can combine together a flight mode and a ground mode, if you like, with a small, this is a simple, very minimally actuated robot with it's actually got just one set of motors that drives both the wings and the legs. So it's in contact with the ground, the legs work. Once it lifts off, then the wings work. So very simple, minimal actuation. Okay, good shape here. So just to summarize things, this is where we're headed. We want to have dexterous mobility, large numbers of robots, quickly map out, penetrate. So the speed is good. Imagine there's people trapped in there. So making something that's very, very effective in terms of finding people and also in terms of battery life. Go through a very complicated environment. There's going to be lots of robots that get stuck along the way and don't succeed, but that's okay because you have a lot of them. And we think that this maneuverability, as we mean it in 2 and 3 dimensions, is going to be really, really important. So just getting close to the conclusion here, this is sort of our current vision. This is work with Professor Cpar. We're building up a 3D map as we go along. So there's a 3D map as the robots are moving. At the very lowest level, they'll have a simple laser scanner on it. So this is, the idea here is about a 5-gram laser scanner. The off-the-shelf ones are typically up at about several hundred grams, a little bit too big for our robots. So a very, very small one. But they can direct the lights. You can see with the camera. Cameras fit on there very easily with a cell phone camera. So we can find the spots. We can work out the geometry. That information is transmitted through local radio back to processor. This robot's got basically a cell phone sitting on it. It weighs about 300 grams, running ROS and all that good stuff, and can then use Wi-Fi to communicate out to other levels. Right, so this robot will control about 10 of these small ones, building up a map. So we have a map here. We kind of know maybe about there's a slope, there's a distance, slope up, slope down, a hole. And somewhere in here, it's a very, very interesting box. So everything I've shown in the talk up to now is that multi-robot locomotion control, where we have to figure out from the map of the surface how to make a plan for the robots to actually go and explore the area they haven't been in before. So I think that's going to be really interesting to work all that out. Great. So then I'd like to thank you for your attention and thank my great group of students who've been putting all these robots together the last 10, 15 years. So thank you very much.
We've been seeing this theme in the last couple of weeks that of guaranteeing safety, of trying to avoid any danger zone or any possibility of a failure mode. But you're taking a very different approach. That if you have enough redundancy, that failures are okay and actually even good in the sense that we're putting out these beacons that get stuck in the quicksand to various spots. I'm curious about that in the sense of, it does seem like there would be, given that you have these relatively low-cost robots, that it actually, that not only for quicksand with mobility, but it does make sense that you would kind of send some off, in these heroic efforts to sacrifice themselves. But by getting caught or something going into a distant corner, then they can serve as a beacon for the other ones. So is there an element of that they would actively go to an area that's, let's say, very dangerous or something like that to...
So there's, in terms of heroics, if you've got an unlimited number of robots, one of the most heroic things you can do is to fill in a hole with your body. So you got a void, and so rather than having a fancy plan to go down in the void carefully with your rope, and rope up on the other side, and you're like, okay, let's hey, any volunteers? Okay, 10 robots come in here and fill up the hole for me. Yeah.
Interesting. Okay.
Yeah, but these dangerous areas. So the other thing is, I'm not sure. Thinking about how do we? I'm not sure from a 3D map or from a camera even that you could really know that something, how is an area really dangerous. For example, like this is what we thought of the quicksand. It's just you got a light there and you just see some flat surface, but it could be dust. Right. It could be covering on something like that. So you may not get the information from the sensors anyway. The other thing is like really small wires and things like that may not show up on your laser scanner. So really, but like if you have a wire coming down, that'll stop your robot.
I mean, I think in some cases where there may be heat or thermal information, right, that would tell you something is dangerous.
Yeah, but you might still need to go through there. So if it's on, okay, this area is on fire, but there might be someone beyond the fire. So you just, you're not going to stop because your robots are. It doesn't matter if you've got basically 30 minutes till your batteries run out, and this is like the vision here is it's a one-shot thing, right? There's some disaster, an earthquake,
right.
And you take your bucket of robots and tell us if there's anyone here in the next 30 minutes.
Right. So there's some collective objective that you're trying to maximize, right? But it doesn't matter individually; it may be sacrificed. It's a very interesting way of thinking about this motion planning.
Yes, it's very high value information, and so you can do a trade-off between
the cost of that,
losing
one or two,
or you can so you can gain overall mobility as well. Like if you find a shortcut, for example, so your heroes go out there, and 10 of them fail, but one finds a shortcut, and now the rest of your robots can explore some space. So it's actually a pretty interesting optimization problem there. You got optimization of information and energy and cost of robots.
Right, and you can do it in parallel because you have these multiple teams. I also like the idea that there's this hierarchy that you have a whole different set of robots that would have to coordinate, and one or two at the base that really you want to protect.
Yeah.
Good. Other questions? How does it relate to other work that you're doing already? Warren, I know you're working on ergodicity. Is there a relevant concept here?
Well, your question about seeking out dangerous areas kind of made me think of if you have maybe not so certain notions that certain areas might be dangerous and might not be. Now you have this whole group of robots, and so maybe you can statistically distribute them in some way that would be useful, as opposed to going towards a particular point. But
yes, we don't. So particular point. I'm not sure how we get that. So we have this random map that's unexplored. So you can go to. So the known points have very little value. It's the unknown points that you don't. But you don't know that they exist. So there's, you know there's a footprint that the building was in, but you don't know that there's actually any reachable space there. So it's kind of, it's interesting that there may be a point there, but it might be pancake, so you can't get to it.
Right. Yeah.
Yes. Have you actually integrated any of the sensors on your robots, like gas sensors or, you know, something like that to monitor the environment and stuff, other than cameras only?
We've had cameras, we have gyros, accelerometers. The couple years back, we got these nice IR sensors that do so you can tell if a person's walking there, and that those seem to work pretty well. They're if I recall correctly, they're 8x8, and so they can tell at about a 1 degree Fahrenheit resolution, so you can tell the difference between someone at the background at 80 and a person at 98.8.
Sensors like gas sensors or
Those are the
thermal
gas
sensors and stuff like that.
Oh, so the thermal we've tried that. The gas is pretty interesting because one of the things we've seen is that they all have very long time constants, and so they have some of them will turn on quickly, but they'll turn off very slowly, which makes it actually fairly challenging to use those. We hope some of those will be available. One of the things I think is more practical, something like a microphone. So that's very easy to put on, because then someone's shouting or something, you can easily detect that.
Cool. Thank you.
Yeah, sound seems like it's very important in this kind of setting, right? That you would want to both sense sound, but also maybe make sounds in some way to communicate. So they could have the speakers and
you could have just bring in the cell phone, and that's actually what the rescuers do now. They drill a hole and they they drill a hole about 3 inches in diameter. They find someone buried under there, and they stick in this container, and the container contains a bottle of water, cell phone, and like a dust mask, and some safety goggles. So they come in with the jackhammers. Really? But the key thing is the water and the cell phone, because once you get the cell phone in there, it's like the difference between I'm lying here, does anyone know I'm here, and hi, how you doing, and wow, that's just a big boost.
Yeah. Oh my God.
Yeah.
How do they get serviced out there?
Well, once they got a tube, they can just
Only getting 2 bars then. Okay, great. Thank you, Ron. This is terrific. Should also mention that Ron's students have started the company that Dash Robotics, which is in. Yeah.
Their initial lab down there.
Great. Okay, and I think they're going to do a talk. We have invited them at least to set up a talk in one of the sessions. Great. Okay, Chen Li is postdoc.
Yes.
Postdoc. So he has been working both with Ron and also with Bob Full, who's in our Department of Biology. And we should know that Bob is away this semester. He's on sabbatical at Georgia Tech. So he's out for the rest of the semester. He'll be back after that. And Chen Li has gallantly offered to come in and give a talk. And he is, I will say, I think it's public information. You're heading off to Johns Hopkins?
Yes.
Great, to join the Mechanical Engineering Department. So, but Chen has been working on this really interesting idea that Ron alluded to, and we'll let him tell you about it. Chen.
Yeah, thanks for the opportunity to talk about my research with Bob and Ron here on the pterodynamics of locomotion in complex terrain. So robots are on the verge of becoming a major part of our society and help humans perform many critical tasks. And particularly over the last couple of decades, we have seen a burst of a variety of mobile robots that begin to move into the real world. However, if you ask any roboticist, including the ones here, I think we would all agree that even our best mobile robots still can often struggle when they encounter complex terrain. For example, we have ground that can flow like soil and mud, and even Martian surface where the robot can easily become stuck. Or we also have terrain that are composed of multiple three-dimensional obstacles like building rubble or cluttered indoor environment where the robot can also be challenged. by contrast, animals move amazingly well in all sorts of terrain, as you can clearly see from these examples. And one of the main challenges that have prevented us from having robots move as well as animals in complex terrain is that, unlike for flight and swimming, where we have the well-established aero and hydrodynamics to allow understanding and prediction of forces and movement, our understanding of terrestrial locomotion has been largely limited to that on on simple surfaces such as flat, rigid ground. These models, while have been very successful in enabling robots to move on these surfaces, they don't capture the interaction, the complex interaction that can occur in complex terrain. Or in other words, we need aerodynamics. So starting with my PhD at Georgia Tech, working with Dan Goldman, we began studying legged locomotion of both animals and robots on a type of ground that can flow, which is granular media, such as sand. And by integrating biology, robotics, as well as physics study, we created the first aerodynamics that can quantitatively predict forces and movement during legged locomotion on sand. And then I moved to Berkeley to work with Bob and Ron to begin to expand aerodynamics beyond granular environment. So what we have been focusing on over the last 3 years is on locomotion through three-dimensional multi-component terrain. So you can see from these examples that there are many cases where we have such complex three-dimensional obstacles where we want robots to be able to effectively go through and help us. And this has certainly attracted a lot of attention. For example, the DARPA Robotics Challenge. But still, our robots don't move quite so well in them. And one of the main reasons for that is that when robots deal with obstacles, they often try to actually avoid obstacles rather than traverse them. And they don't fully take advantage of the physical contact with the environment. And this is largely due to the fact that much of this obstacle avoidance approach had been using models such as the artificial potential field or virtual force field, which are artificially defined to facilitate computation, but are not derived from contact physics. Whereas there are many small animals that can move very well in such 3D multi-component terrain. And we may wonder whether animals really try to always avoid obstacles when they go through them. And or is that even possible when you move at high speeds dynamically? So just to give you an idea how challenging avoiding obstacles can be when you move in such terrain, here is a video that I took with a small robot, with a camera on a small robot running on campus. So here the robot is going through a bunch of dense vegetation and leaf litter, and then it's crossing a street, and you can see a person just walked by. So in fact, these are tiny little things that we don't even think about when we go through at our scale. But for a small animal or robot, they effectively become a dense forest and literally impossible to avoid at all times. So how do animals go through? To begin to understand this, we choose to study this animal called the discoid cockroach from the tropical rainforest, which has to traverse this type of terrain all the time. And also, as a starting point, we decided to pick grass as one simple representative of 3D multi-component terrain. And inspired by the wind tunnel and flow channel, which have allowed repeatable experiments for studying flight and swimming, we then created this device using laser-cut paper assembled into arrays to mimic grass. So now we can precisely control and systematically vary their geometry, spatial configuration, and mechanical properties. And with our device, we decided to challenge our cockroaches to go through beams that are taller than twice their body width with lateral spacing that's less than half their body width. And how does the animal go through? So here's a typical trial. And as you can see, the animal runs into the beam and crashed into it, and then it tried to push its way through the first couple of layers, then started climbing up and fell forward and traversed. And this trial took about 4 seconds. And here, and this is the locomotor mode sequence for this particular trial. And in other cases, we observed that the animal can move through much faster. So here's another trial, about 1.5 seconds. And you can see here, instead, the animal would push forward and then roll its body towards the side and slip through the narrow gaps between beams. And again, here's the locomotor mode sequence for this trial. So now, these are the 2 trials you have seen. And with our apparatus, we can then do this repeatedly for a couple hundred times. And then here's what we got, a complex locomotor transition diagram. So the animal starts from here and then uses one or a sequence of a variety of locomotor modes to traverse. And these the thickness of these lines are proportional to the probability of transition between modes. So you can see that the animal is capable of doing using a very diverse locomotor pathways to go through. But among this diversity of locomotor modes, it in particular uses this pathway by performing the roll maneuver to go through, which is about two-thirds of the time. In addition, when we measure the time that it takes, the animals when the animals does that, it's the fastest, taking about 2 seconds on average. Whereas if the animal uses any other modes, then it takes on average over 5 seconds. So clearly, the animal has somehow figured out that this is the most effective way to go through. And now we were wondering what our robots do. So we tested Velociroach, which is one of the fastest robots running on open surface at about 20 body lengths per second. And as you can see here, the robot very rarely traverses, but often becomes stuck, even when the opening between the obstacles is wider than its body width. So instead of rolling, the robot would turn to the left or right as soon as it hits the beam and becomes stuck. So we were wondering why the animals are so much better than the robots. And when we observe them, one obvious difference, as you can see here, is their body shape. The animal is well-rounded with this resembling a thin slice of an ellipsoid, whereas the robot is highly angular with corners, straight edges, and flat faces. And here, again, considering that here the animals and robots are actually pushing through terrain which can push back against them, which is similar to when you are moving in fluids with the surrounding environment pushing against you. So we were, again, inspired by this phenomena in fluid, the well-known streamlined body. So we hypothesized that maybe such well-rounded shape is pterodynamically streamlined and can help reduce resistance in the terrain and facilitate traversal. And how do we test our hypotheses? So we gave our cockroaches backpacks by systematically reducing their roundness while controlling the overall mass, volume, and friction of the backpack. We found that, as we expected, as the body roundness reduces, the animal indeed less and less frequently uses this most effective roll maneuver, and that results in lower traversal probability and longer time. So having discovered the pterodynamic streamlining concept, we then used this as a bio-inspiration and added a thin rounded shell to our robot. Now, without adding any sensors or changing the control of the robot, it can simply push through the beam by performing this passive roll maneuver, even when now the gap between the beams is wider than the shell width. And we have also begun developing a very simple model to begin to gain insight into this shape-dependent locomotor-environment interaction. So for example, if we can think of two adjacent beams as simple rigid plates with torsional springs at their base so that they can rotate in the fore-aft direction. And then we can also simplify the animal or robot as a rigid body. Now, for each position of this object in the horizontal plane, as well as each of its orientation, we can then determine how much it will displace the beam, and then write down the total potential energy of the system that results from gravity as well as elastic bending. And then we can calculate we can minimize this energy over the rotation degrees of freedom that will give us for each position in the horizontal plane, what is the orientation that has the lowest potential energy and the corresponding lowest potential energy landscape. And here, as you can see, if the object is right in the middle of the two beams, then its lowest potential energy orientation would be flipped on its side. Whereas if it's closer to one of the beam, then its lowest potential energy state orientation would be pitching up. And these corresponds with our observation of the animal and robot doing roll maneuver and climbing. And further, we can also begin to gain insight into why this depends on shape. So when we compared this locomotion energy landscape resulting from a rounded ellipsoid with that from an angular cuboid, we can see that the angular cuboid not only gives you a higher potential energy barrier and narrower valley, but also if you look at the cross-section and take a derivative, you can see that for this angular cuboid, it results in repulsive forces away from the middle unless you are right in the middle. Whereas for the rounded ellipsoid, it gives you attractive forces towards the middle. And this, again, corresponds with our observations. And finally, with the advent of cloud robotics, the expected advent of cloud robotics, in which robots will share information through the cloud, we envision that this new approach of pterodynamics will complement the well-established sensing-based mapping and path planning and become a critical part of the cloud robot environment interaction databases and guide our robots to perform a variety of tasks in the real world. So with that, I would like to thank my advisors, Bob Foe and Ron, and also Dan Goldman at Georgia Tech, and the members of the 3 labs that I have been part of, and my funding sources. And also, I would like to take this opportunity to make a pitch that I will be starting my lab at Johns Hopkins. So if there are anyone here, or if you know anyone who might be interested to work on these topics, feel free to contact me, and you can find more information on my website. Thank you.
Thank you, Chen. This is really interesting work. And in the models that you have, I was curious about the degree to which you work to optimize the shape. Can you say a little more about the specifics of that, the ellipsoids, trying to optimize? I mean, did you look at a whole range of possibilities?
No, not yet. So,
okay,
yeah,
so that's still to come.
Yeah, this is just the first step. Yeah.
Great. Okay.
Yeah, and that's something that I plan to do, to use these robots as a physical model. So, like in the animals, we can only modify their shape to a certain degree, and that often will affect their behavior. So we want to use robots to do more systematic variation. Yeah.
And I'm curious, these are experiments physically? Are you actually doing it in simulation or in physics? Physical?
You mean these?
Yeah.
So these are so they're not like a dynamic simulation yet. Right now they're just sweeping the parameter space and calculating the energies. Yeah, but so if you assume that everything results from passive mechanics, then I imagine that one can then go do a forward simulation, dynamic simulation, and calculate the trajectories.
I mean, actually, simulating is non-trivial for these kind of scenarios,
Yeah.
right? Also, but I'm just curious. Can you build a? I mean, is that one of your intentions, to build a dynamic model, dynamic simulation for this, and see if we can recreate those experiences?
Yes. But I think that it will have to be grounded to experiments. Like I wouldn't believe it by itself.
Good. Actually, that's a really, because I was curious about that with Ron too. To what degree do you use simulation to optimize on the parameters?
We're so dependent on the ground mechanics, and that's the hard part to model. So it's like the part we can't model almost overwhelms the parts we can model.
Right. So the contact mechanics and all the coefficient of restitution and all that stuff, especially with this.
Just stubbing your toe. So in the simulation, fine, you got nice planar surface, but you bring it out just even on the carpet here, you stub your toe, and suddenly the robot will take a 30-degree turn.
Right. Which is it. Okay. So, I mean, because even in the physical experiments, when you're trying to do, let's say, optimization, you could imagine that, right, you putting these different ellipsoids onto the back of a physical robot and then letting it run through these trials. There's an interesting sort of optimization process there, too. How do you choose the next thing to try? Because it's fairly costly, each experiment.
Yes. So definitely simulation approach is one of the tools that I intend to develop further. So my PhD advisor, Dan Goldman at Georgia Tech, he has mostly been focusing on studying, like doing this for granular environment. So we had a few students kind of basically develop the discrete element simulation of granular materials from scratch that's validated by experiments. So now that has really become very powerful, like accurately predicting the forces and movement. But one of the insights that we have gained through studying that, as well as this system, is that it seems that when you have highly damped terrain, such as granular media and here these very densely cluttered beams, then it seems that they will become more dominant in determining the dynamics, whereas if you just run on open ground, then the hybrid contact turned out to be actually more difficult to model. When you have these highly damped terrain, at least in the granular case where we have already made progress, it turned out to be easier to understand. Yeah.
Other questions? Yep.
Yes.
So with these experiments and energy surface calculations, have you tried varying the mechanical properties of the obstacles or maybe the geometries of the obstacles? And do you think that you would see different behaviors if you did?
Yes. I did a little bit of that. For example, so here really this, what you're seeing here, as I mentioned, this is a potential energy that results from both gravity and elasticity. So what's being shown here in this case, it's dominated. This surface is dominated by elastic bending. So that means the beam is stiff enough so the robot or animal really is like injecting a lot of energy when pushing on it. But if for example, if I choose a stiffness that's much smaller compared to, so gravity would become dominant. So in that case, in experiment, I have tested like very flimsy beams made from regular paper. So these are actually like very thick cardstock, but with a very thin paper, the animals and robots can just walk through without being affected much. Yeah. Yes.
How do you put jackets on the cockroaches?
Oh, so
glue them?
yes. So the animal, the body has some flexibility, but this part of the exoskeleton is really rigid. So we just had hot glue to glue on top of them.
I mean, I assume that it will actually help with the sensing capability, right? I think you're right. So we try to put it so that it doesn't extend much beyond their exoskeleton. Yeah, but we have also done some preliminary experiments cutting off the antennae, and they can still do it, but it seems that they don't do it as well, and also it affects their behavior. They actually hesitated a lot. Yeah.
What do you think the antenna is doing there? I'm curious.
Oh, so let me go back to this video. Yeah, I think it's probably detecting, oh, there's a gap, so maybe it's helping it initiate that roll. So the animal, they can, when they do this, you can see this gap is much narrower than their body width. It's actually barely wider than their body thickness without the legs, but they can still do it very well. Whereas the robots, really, we have to tune it. The gap size has to be well tuned so that the robot can go through. So I think that the animal is probably very likely doing some active adjustment as well.